So let's talk about quantum computing. Right now, the whole industry is kind of caught in this fascinating paradox. On one hand, it promises to literally change the world with computing power we can barely imagine. But on the other, the multi-billion-dollar machines that have actually been built are, well, really struggling to prove their worth. So what's actually going on here?
In this explainer, we're going to dig in, almost like a forensic investigation, to try and answer that exact question. We're going to look at the hard technical evidence, and we're going to follow the money to see if this revolutionary technology is standing on solid ground, or if it's all just a massive bubble that's waiting to pop.
All right, so first up, let's examine the central conflict that's really at the heart of this entire industry. It's this huge, gaping chasm between the incredible future that quantum promises and the much, much harsher technical reality of today.
I mean, the promise is nothing short of exponential power. But the current reality? It's defined by what everyone in the field calls NISQ. That's Noisy Intermediate Scale Quantum Machines. And the key word there is noisy. These things are just crippled by errors, which severely limits what they can actually do. They're supposed to solve unsolvable problems, but in some pretty high-profile cases, they're actually getting beaten by high-end gaming hardware. Yeah, you heard that right.
And that brings us to the core technical challenge. It's a phenomenon the source material calls the simulation win, where classical, normal computers are consistently beating their quantum rivals at tasks they were supposed to be perfect for. So you have to ask, why are these regular computers winning? It's not just about having faster chips. The secret weapon here, the unexpected hero of this whole story, is a really, really clever type of algorithm that has completely changed the game.
And that secret weapon is called a tensor network. The easiest way to think about it is like a hyper-efficient compression tool for quantum data. It lets a regular computer find these incredibly clever shortcuts to simulate massively complex quantum systems, something that, for a long time, we thought was flat-out impossible without a real quantum computer. So here's the crucial point, the part that's kind of hard to wrap your head around. Thanks to these tensor networks, the main competitor for a multi-million-dollar quantum computer is, in many cases, a high-end consumer gaming GPU. An NVIDIA RTX 4090 can actually simulate systems with over 100 qubits faster and a whole lot cheaper than waiting in line to run a job on a real quantum computer.
Okay, so if today's machines are so handicapped, what's the solution? Well, the industry does have an answer. Building what are called fault-tolerant quantum computers. But getting from where we are now to there requires crossing this monumental engineering chasm that we're going to call the million-qubit gap.
The only path forward that we know of is something called quantum error correction, or QEC. The basic idea is brilliant, really. You use a whole bunch of unstable, error-prone physical qubits to create a single, super stable and reliable one. It's a great idea, but it comes at an absolutely staggering cost.
See, before you can even think about doing error correction, your basic physical qubits have to be incredibly high quality. This is what's known as the fidelity cliff. Your components need to work correctly at least 99.9% of the time. If your error rate is any higher than that, the very process of trying to correct errors actually introduces more new errors than it fixes, and the whole system just falls apart. Just look at this table. It shows the immense overhead we're talking about. To create just one of those stable logical qubits, you need thousands of the unstable physical qubits. Take a look at that middle row. Even if you hit that 99.9% fidelity, that 3 nines of quality we just talked about, the ratio is still 1,000 to 1. You need 1,000 physical parts just to make one working logical part.
And that leads to the staggering number.
To build a quantum computer that's actually useful, something that could solve major problems and needs around 1,000 logical qubits, you would need over 1 million physical qubits. That's the million-qubit gap. And right now, the biggest systems we have only have a few hundred. We're not even close. Bridging that gap means solving engineering problems that honestly sound like science fiction. For superconductors, you've got to figure out how to wire and control millions of components inside a refrigerator that's colder than deep space. And for the other big approach, trapped ions, you're fighting their incredibly slow processing speeds and trying to master a brand new, totally unproven type of laser networking.
Okay. So with those immense technical cliffs laid out, we have to turn our investigation over to the money. Has the financial hype just gotten years, or maybe even decades ahead of the actual science?
This chart paints a really stark picture. It uses a key metric called the price-to-sales ratio. Now, a big mature tech giant like Google might trade at around 6 times its annual sales. Fair enough.
But in contrast, the leading public quantum company, IonQ, has been trading at over 100 times its sales. That is a valuation completely disconnected from today's reality. It's a classic bubble indicator, what investors call being priced for perfection.
When you have an extreme valuation like that, combined with all the technical skepticism we've just talked about, well, you know it's going to attract a lot of scrutiny from investors. And that led to one of the most high-profile battles in this industry's recent history.
So back in 2022, a short seller called Scorpion Capital put out this scathing report basically calling IonQ a hoax. That immediately triggered a class action lawsuit for securities fraud. The whole thing worked its way through the courts and was, in the end, dismissed by a federal appeals court.
But the crucial point here is why the court threw the case out. The judges decided that IonQ's really optimistic statements weren't fraud, but legally protected puffery. That's a legal term for exaggerated marketing hype that isn't really meant to be taken as a literal fact. So while it was a legal win for IonQ, it really shines a spotlight on that very fine line between selling a future vision and misrepresenting the present.
Now, that financial risk isn't spread evenly. A company like IonQ, for instance, is sitting on a massive pile of cash, which gives them a runway of over 5 years to keep doing their research. But its smaller competitors, like Rigetti and D-Wave, are burning through cash much, much faster. They might only have a couple of years left before they have to raise more money. And that's going to be a really tough thing to do if the market sours on quantum.
So, what's the verdict of our investigation? Well, when you put all the evidence together, the technical hurdles, the crazy valuations, the solvency risks, it all points to a pretty severe industry correction. A so-called quantum winter seems highly likely.
But here's the great irony in all of this. To survive, the industry is making a pivot. A lot of these companies are now selling quantum-inspired software. You know what that is? They're using those powerful tensor network algorithms, running them on classical GPUs, and selling that as a service. So in a way, they're selling the very tools that prove their own quantum hardware is often unnecessary right now.
This coming winter is probably going to trigger a massive consolidation in the industry. The survivors will likely be the ones who can just afford to wait out the storm. We're talking about the tech giants, Google, Microsoft, and the pure-play companies with fortress-like balance sheets like IonQ. The smaller, cash-poor players, though, they face a very real risk of just not making it.
Now, let's be super clear. This fallout, this quantum winter, it's not going to be a rejection of the science. Quantum mechanics is real. The long-term potential is absolutely still there. What this is a rejection of the wildly unrealistic timelines that the market has been sold. The bubble isn't in the physics, it's in the schedule.
And so, that's where our investigation concludes. A quantum winter is coming. It's going to be a brutal test of technology, of engineering, and of financial discipline. The real question isn't if quantum computing will eventually arrive, but rather, who will be left standing when that fault-tolerant spring finally dawns?